G'day and welcome to the first video for Module 2 Dynamics. In the first module, our focus was on kinematics, and that was all about describing, measuring, and predicting motion. In this module for Dynamics, our focus is going to be much more on why motion is caused and being able to measure the causes of motion. In this first video, we're going to be covering the basics of forces. A lot of it is going to be revision, and it is reflective of dot point 2.1.1, the first dot point of the module. First off, this is our first inquiry question here. How are forces produced between objects and what effects do they produce? So what's being implied here is that, generally speaking, forces are the cause of motion, and we're going to be unpacking force interactions and what that does to motion. We're going to be unpacking the things that actually make forces. And to start, for our first content statement, we're looking at this idea of Newton's laws of motion, which is a concept learned about in year 9 and 10. We're also going to be focusing on static and dynamic interactions and scenarios. And we're going to be focusing on contact forces and field forces. So to begin, our learning intention for today is essentially to review a lot of the concepts that are included in that first content statement. So looking at ways to describe, classify, and graphically display forces, as well as look at Newton's laws of motion and come up with some examples and applications. On top of that, we're also going to be looking at defining a few key terms relevant to this dynamics topic. So first off, forces. Basic definition is just something that is able to influence an object, causing an acceleration. This means speeding something up, slowing something down, or causing a change in the direction of motion. This is a vector quantity, meaning that forces have a magnitude, a size, but we can also describe them with a direction. And whenever we look at forces, they are measured in newtons. So there are 4 core types of forces that will come up in a lot of problems in this module. There are more forces than that, and we will be looking at applying those forces to different scenarios. But the key ones are an applied force, so a force put on an object by another. For example, pushing on a box would be an applied force. There's also gravitational force. Generally speaking, we're focused on looking at the gravitational field of the Earth, and that force is always bringing objects closer to it. We also have a normal force, which I will break down in a little bit more detail as we go along because it is related to a few other physics concepts, but it is one that you're going to start seeing a lot in this module. And we also have friction, and friction is a resisting force when 2 different objects or substances are in contact with each other and moving across each other. So first off, this idea of contact and non-contact forces. Definition-wise, it's pretty straightforward. If objects or substances are in contact with each other and they're applying a force on or between each other, then we label them as a contact force. If there is just a field that's leading to a force and there is no direct contact between objects, we call it a non-contact force. Some examples of contact forces you may come across in this module are muscular forces. It's probably not the best word to use, but I guess that just helps to define forces that can be caused by people. There are also frictional or resistance forces between solid objects or liquids and gases. Spring forces, where an object undergoes a force because it's trying to return back to its original shape. Tension forces, which exists when things like strings and ropes are pulled. Thrust forces, which propel objects forward. And as well, again, normal forces are contact forces. I'm going to be talking about them in a little bit more detail later on. So first off, next thing I want to cover today is Newton's laws of motion. There are 3. These are things that you should have covered in either year 9 or 10. The first one here, a lot of the time we talk about this concept of inertia, and that's very much associated with Newton's first law. Generally speaking, when we look at the definition of Newton's first law, there are 2 statements that sort of cover it. The first one is that when an object is at rest, it remains at rest until an external force acts upon it. In this case, our example here is our cat and the glass. The glass of liquid is at rest until the cat decides to put a force on it, causing the glass to move. The other statement is that an object in motion remains in motion. In other words, it has a constant velocity, so a constant speed and a constant direction, unless an external force acts upon it. A really good example is to think about objects moving in space. So these asteroids here will essentially move at a constant speed in the same direction continuously until there is some other external force that acts upon it. Generally speaking, if we are looking at a cluster of asteroids, that external force will probably end up being a collision between 2 of those objects. Something to reflect on though, this second statement has a little bit of a limitation when we look at the Earth. So on Earth, forces must always be applied to maintain constant velocity of an object. Now I want you to have a little bit of a think to yourself of what the cause of that might be, why there must be forces applied to objects to maintain constant velocity on Earth, and we'll have a little bit of a chat about that in class. Some other examples of Newton's first law. In this example here, we've got a little bit of a car crash animation scenario happening. Essentially, what's being shown here is that the person is moving at the same velocity as the car until the car crashes into the wall. The car decelerates, but there's nothing that's happened to the person to cause a deceleration there to slow it down. So in other words, that object, the person, remains in motion, or at least a higher degree of motion than the car, until there is an external force which will end up stopping that motion. In our second example here, what this shows is that objects in rest tend to stay at rest unless an external force is applied. So in this example, the board that is underneath the cup has a large amount of force placed upon it. It's able to clear across those cups of water, but the tennis balls don't really move with that same velocity as the board. Instead, they effectively just drop straight into the cups. Now, there is a little bit of a force that pushes the tennis balls a little bit away from the glasses, but not enough to have them fall away from the cups. And so this, again, is an example of where objects at rest generally stay at rest unless an external force acts upon it, effectively meaning that really only gravity was the force that was causing motion once the supports underneath the tennis balls were removed. Our next law is Newton's second law. Essentially, this law talks about the acceleration of objects. And the law says that it's dependent on the force applied on the object as well as the mass of the object. There's a statement here, a mathematical statement. You may not be so familiar with this symbol in the center. It's just the Greek letter alpha, but this says here that acceleration is proportional to a force vector. Essentially what that means is that if acceleration is to increase, then that means there was a larger force or an increased amount of force placed on the object. In the other statement that we have, it says that acceleration is inversely proportional to mass. In other words, it's proportional to 1 divided by mass. And instead of there being this increase relationship, what we can say is that if acceleration increases, then it could be because mass has decreased in the object, or the mass is smaller in the second object. In both of these examples, when we're talking about proportionality, we're assuming that the other variable, in this case mass, and in this case force, is constant. I'm going to spend a little bit more time in class going over this idea of proportionality and using some dummy measurements, I guess, to show how that mathematical relationship works. But when you put both of those proportionality statements together, you can actually write up an equation that looks like this, and that is F equals ma. The force applied on an object is equal to the mass of the object times the acceleration that's caused as a result of that force. And this is the main equation that summarizes Newton's law. Now, in the GIF that we have down the bottom, we have a little bit of a contraption which is able to have a foot drop on two different ball-like objects, a bowling ball and a balloon. And in these two examples, we're assuming that because the foot, or the dummy foot, has been dropped from the same height, that the same amount of force is being applied to both objects. But what we can see here is that the object with less mass essentially accelerates more. The object with more mass accelerates less. Now, the formula for Newton's second law, F equals ma, does feature on your data sheet, so it is something that you can always refer back to. You will notice too that it does say F net, or force net. We are going to talk about that concept in this lesson to start off with, but then in further detail in coming lessons as well. What I also want to look at is this idea of gravity and Newton's second law. When we're on Earth, gravity plays a really big part in looking at the forces that are being applied to an object and thus its resultant motion. And we can look at the force of gravity by using a really key piece of data, which again is on your data sheet. This is on the first page where all of your constant values are. Now, Earth's gravitational acceleration g is 9.8 meters per second squared. Essentially, what that means is for any object, the pull of the Earth will accelerate an object by 9.8 meters per second squared, regardless of how much mass they have. That's always just going to be how much an object, a body, will accelerate due to the pull of the Earth. Now, with that in mind, we can apply some of this information to our F equals ma formula. Essentially, the force due to gravity, which sometimes you'll just see as Fg instead of using the full word for subscript, that is equal to the mass times g. So the mass of the object times the acceleration, which is 9.8 meters per second squared. So a lot of the time you will see formula when you're looking to try and find the force on an object due to gravity, Fg be equal to simply mg, the mass of the object times the acceleration of gravity, g. Something else to keep in mind is that because we have acceleration in this F equals ma formula, we can use or show different units of measurement for A, and I'm going to show you how that works. I will note that this is not something that you usually see or represent A for in terms of units of measurement, but technically it is a representation that you can show, and again, it comes from this F equals ma formula. Now, an alternate set of units of measurement for acceleration is N per kilo, newtons per kilo. Now, when we write F equals ma, we can rearrange that formula so that A is the subject. In other words, A is F on m. Now, like we've done previously, we can show what the units of measurement of a variable in a formula is simply by substituting in the units of measurement for all of the other values on the other side of the equation. So in this instance, we can put in the SI units for force and mass. Now the SI units, as we said before, for force is newtons, and the SI units for mass is always kilograms. In other words, the units of measurement for it is newtons per kilo. That's just a little bit of a tidbit. It won't really come up too much within the scope of this course, but I think something that's really important to reflect on and know as we build our skills in being able to apply our understanding of units of measurement as well as physics equations. The third and final law, Newton's third law, a lot of the time gets read out or talked about as with every action there's an equal and opposite reaction, or some very similar sentence like that. It's not, I guess, the best representation of what that means from a physics perspective. I think a little bit of a better reword would be something like when a force is applied to an object, the object exerts a force which is equal and opposite in direction. In other words, the force of A on B is equal to the negative force of B on A. So in the example that we have down the bottom, we have someone crashing directly into a wall. There is a force pair first off between the bike and the wall, and then a force pair between the person, especially their head and upper body, and the wall itself. So just to show that a little bit diagrammatically, what we could draw is a side view of the wall itself, and then we could have a person crashing, say, into the wall. And here we would have a force person on wall, so FPW, but there would also be a force where the wall is exerting an equal but opposite force on the person. So force wall on person. Now, when we start to do a little bit more complex force analysis than what you would have been used to from years 7 to 10, the application of third law is actually really important in being able to understand what forces are, where they are, and how they influence the motion of objects. Something really important to note as well, a lot of the time, these kinds of forces that we see, an action-reaction kind of force, will just simply be referred to as a force pair, and that will be reflective of the concepts covered in third law. Next idea that I want to talk about is this concept of net force, and that is the result of combining forces together. We will unpack this in more lessons to come, but I just want to remind you of the idea that when we have two or more forces acting on an object, the net force is just the result or combination of them. So already we've been using vectors to find resultants for things like displacement and velocity. We will be using those same kind of concepts here when looking for resultant forces. Now, a simple one just to begin with at the moment is, let's say this box was pulled with 15 newtons of force and push from the other end with 10 newtons of force, the net force, F net, would effectively be equal to a force in the same direction, but a combination of the two. Here, it's just a simple addition of 25 newtons. Now, obviously, when we start adding the second dimension and trigonometry concepts, calculating net force will be a little bit more involved than a simple one-dimensional example, but that is just the general concept of net force for you there for today. And I'm going to use that idea to talk a little bit about equilibrium, balance, and unbalanced forces. Now, in physics, equilibrium exists essentially when there is no change in motion. It's really important to realize, I think, that equilibrium is a word that gets used a lot in a lot of different scenarios across a variety of different sciences. But here, when we're talking about motion and in physics, again, with equilibrium, we are really focused on this idea of no change in motion. So essentially, when forces are balanced, that means that the net force is zero. When the net force is zero, there's no force being put on any direction on the object, meaning that there won't be a change in motion. In other words, there is no acceleration. Now, the GIF that is on the left here with the tug of war, not too sure why that is not working, but essentially what's being shown in this little clip is that the school kids in The Simpsons are pulling on the rope. They're grunting, they're trying really hard to get the rope to move, but effectively here there is no net force. They're pulling and pulling and pulling and getting nowhere. There's no movement that's happening. Because there's no acceleration, the net force is equal to zero. Here in this example between Homer and Apu, we have a net force that is not equal to zero. There is a continual change in motion and acceleration in one direction and then another. Apu and Homer are taking turns in applying a greater force than the other person, meaning that that is leading to, again, a non-zero net force, one to the left and then one to the right over and over again, causing accelerations in both directions. Something else to focus on is this idea of static and dynamic equilibrium. When static equilibrium is occurring, the net force is equal to zero, and that means that the object is at rest and it continues to stay at rest. This example on the left is an example of static equilibrium. In this scenario, what we have are forces caused by gravity on both the box and the table, which are pushing both of those objects into the ground. But because of Newton's third law, we have the ground pushing back up on both of those objects. And that action-reaction pair that we have, this force pair, are effectively equal and opposite. So all of the down force is being counterbalanced by all of the upward force. And because when you add all of those forces together, the net force is zero, we have this point of equilibrium. And again, we call it static equilibrium because the object is at rest and continues to maintain its rest. However, there can also be dynamic equilibrium. Scenarios, again, where net force is zero, but the object is in motion, meaning that the object is at a constant velocity. Here we could imagine a dynamic equilibrium with a plane. In other words, the plane is moving at a constant velocity forwards. And that's not just in the forwards direction, but also in the up, down, left, and right directions. So when we look at the balance that exists between, say, thrust and drag, the aeroplane would have a thrust force which pushes it forwards in a way which is equal and opposite to the drag that's being caused by air resistance. If those two forces are balanced, then there's not going to be an acceleration or a deceleration forwards. Similarly, you could talk about the balance of the plane, not that this diagram shows it, but a balance of the plane would ensure that there is no left or right motion in any way. The other force pair that we have here is a balance between lift and weight. So as the aircraft is moving through the air, there's always a lift force pushing upwards, and this should be countering the weight force. If there is no rise or fall in the plane, what that means is that the lift force and the weight force are equal and opposite. They are balanced, and what that will mean is, again, a constant velocity, a constant speed, and a constant direction when we have a scenario where there is dynamic equilibrium. So they're all the concepts that I wanted to cover today. Again, they are the fundamentals that will underpin Module 2 and modules beyond. In the next video, we're going to look a little bit deeper in applying some of the vector concepts that we learned about in Module 1 to these ideas of forces. I'll see you in the next video.